And today I want to get back into these series tests. And so really, I kind of want to actually break them into group work for a while and just try to just have you guys think about these, just kind of almost try to come up with whether you think it converges or diverges and what tests might be applicable, as opposed to really justifying it within an inch of its life, because we did 1 through 5 last class, right? But let me just remind you some of the tests you think about. The first thing you should do is just ask, are the terms going to 0? Right? That's this first test. Because if not, then you know the series diverges automatically. If the individual terms don't go to 0, then when you add them up, it's going to add up off forever. We talked about these comparison tests. You can use either of these comparison tests that we discussed Monday. Direct comparisons, just like we did with improper integrals, comparisons of improper integrals. And then the integral test is kind of like you can try to, if you can't figure out anything else, you could try to see if the function inside the series is something you could integrate and turn it into an integral instead. Okay, and the other thing I want to say before we break up into groups is that, when we looked at this number 4 here, the n to the 5th over 3 to the n question. And let me go to the board just to say, because there are other ways to do this, but we're going to learn this thing called the ratio test that we could also use on this. But for now, and we're looking at something like this, it really is important to think about how fast certain quantities are growing or how fast things are going to 0. Because that's really what matters here, right? We know, don't forget the p-test also, which I don't have on that sheet, but we know that if something goes to 0, 1 over n, then that series diverges, right? Because the 1 over n series, the harmonic series diverges. But if it goes to 0, 1 over n squared, then it converges. That's kind of one of the 2 main examples you should have in your head, right? But in general, so in general for convergent, maybe I'll just write this case, it's a general comment. In general, for convergence of series, convergence of a series, let me just say sum of a sub n, it matters how fast a sub n is going to 0. Right, if a sub n is not going to 0, then we definitely know the series doesn't converge. But it matters how fast. For example, sum of 1 over n does not go to 0 fast enough. Not fast enough. Series diverges. But 1 over n squared does go to 0 fast enough. So the series converges. Right, that's sort of it's basically how fast is this sum coming to a stop? How fast is it slowing down and coming to a stop? It's almost like a deceleration thing to me. It's kind of strange just to put it that way, but it's and in fact, the p-test even says even if I made this exponent 1.01, that would still be fast enough. So it's really, there's a tipping point at 1, right? And then we looked at this example, number 4 from the series test 1 handout. Sounds so official for something I just wrote. The sum of n to the 5th over 3 to the n. And sometimes I'm being lazy and not writing the bounds of the series, but just always assuming they're infinite. What we said last time was that n to the 5th grows, polynomials grow much slower than exponentials. So when you see something like this, you should have a sort of, you're trying to build an intuition for something that's very not intuitive. It's kind of what a lot of math is like, there's a saying in math that like, you don't ever learn new math, you just get used to it. You just get used to some things being weird. And like, so you're trying to build intuition here. It's like, it's some sort of intuition. So polynomials grow more slowly than exponentials. And by kind of a lot, I mean, by really like in a very significant way, the exponential will grow much faster. So when I see a fraction like n⁵/3 I think, oh, as soon as n starts getting big, this is going to go to 0 rapidly. It's kind of what you think in your head, right? Because the polynomial is on top, the exponential is on the bottom, so the bottom's going to grow faster. It's going to go to 0 rapidly. So yeah, so we would say something like n⁵ is less than 3 for n large. But there's even another notation in math that people use sometimes, which it's not in our textbook or anything, but like sometimes people use like a double less than sign, meaning like it's a lot slower. But I'm not gonna actually get into that because that gets a little bit more complicated. But in fact, really, I could say even something stronger. Like you can make these statements really strong, and that could be helpful. Like here, like let's see. You can make like the statement as strong as possible. Like not only is n⁵ grow like smaller than 3 you could say something like n⁵ is actually less than 1.001 for n large. And this is much less obvious because if you try values of n, it's going to look like this is a lot bigger. Right, if I put in like 10 here, 10⁵ is 100,000, and 1.001 is so small. So you have to like, this is something we are talking about like the first day of the semester when I give you that like sort of like food for thought handout. That like, you know, if as long as you make n large enough, this starts to overtake this. Or you could say, you know, or you could say something like n⁻⁴ is less than, I could say 1.001 to the n, but maybe I'm just changing one of these two things, right? For n large. And the reason I'm saying you want to try to think about statements like this and making them stronger is because I sort of did this kind of abruptly last time, but maybe it's worth like talking about. I can make this an exponential function on top. I can like put a less than sign and put an exponential function on top here. But if I put 3 that's not really good enough to tell me anything because I get 3 which is 1. Right? If we use, I guess I'm trying to think about like what the thought processes are when you see these kind of problems. And you have to have some intuition. Like if we only use n⁵ is less than 3 then the sum n⁵/3 is less than the sum 3 which is a sum of 1, which means you're adding 1 over and over again. Right? 1 plus 1 plus 1 plus 1, which diverges. So this isn't strong enough to tell us anything about this series. You get what I'm saying? Like this is smaller than something that diverges. So not strong enough. But, and what I did when we did this problem in class is I said on Monday was n⁵ less than 2 to the n is also true, right? It's less than any exponential. And if you use that, then I can say, this is what we said last time. And all of a sudden, this is more interesting, right? Because that's the sum of 2/3 to the n, which is geometric with r equals 2/3. So it converges. which means, so that means that this series also converges. So that's what I'm saying. Like some of these you look at, if you look at some of these problems on this sheet, on the series test 1 handout, there are places where this stuff's going to come up. You know, these kind of things will come up, right? And you might want to try to compare it to other things, you know, and try to use a comparison that's make an inequality that will actually be helpful. And I'm saying you can sort of make, as long as you have a polynomial here and an exponential here, you know the less than sign works if, like for n, as long as n gets large enough. Does that make sense what I'm getting at? So that's kind of what I'm going to want you to think about as we're doing these problems. And then I just want to say similarly, because it comes up, there's some that have logs in them, natural logs. So similarly, logarithms grow slower than polynomials. Grow more slowly than polynomials. So, or the powers, I even should say just powers, like then or powers slash polynomials. Because yeah, I guess number 3, we use natural log being greater than 1, but I could say, for example, natural log of n is less than n, right? But I can even say stronger things, or stronger would be that the natural log of n is less than square root of n for n large enough. I mean, in fact, it's probably for all n. But I could even say natural log of n is less than n to the 0.001 power, 0001 power. So like, these are the kind of things you almost want to have in your toolkit for like, oh, I can use these kind of inequalities whenever I want when I'm thinking about an infinite series. And if that helps, you know, I claim that'll help in number 9, for example. If you look at number 9, just thinking about the fact that natural log n grows really slowly. You get what I'm, does it make sense what I'm saying? I could even do like ln of n to the 100th power is less than n to the 0.0001. I mean, I guess there's a question of whether you believe me, but we sort of justify, we could justify these sort of statements with L'Hopital's rule that like this ratio, this divided by this goes to 0. Or this divided by this goes to 0 as n goes to infinity. I'll share a screen in a second, but let's just look at something kind of reasonable. Yeah, so I even think I might have showed this kind of thing in class once this semester, but like if you look at, if you compare natural log of x to x to the 0.1 power, which is like the 10th root of x, it looks like natural log overtakes it, right? Did I do something like this earlier in the semester? Where we can keep zooming out forever. If I keep zooming out, I guess I'm zooming out in the x-axis. Well, this looks bad, right? It doesn't look like, it looks like natural log is a lot bigger than x to the 0.1 power. This is fun to me. This is how I have fun. Oh, wait, sorry. I want to zoom in on this a little bit. Okay, let me zoom out. You can see them rising, right? Like this now is down to 5 times 10 to the 10th, and this is 10 to the 10th. They're both going up, right? Looks like natural log's in the lead. It really is like a tortoise in the hare race. Oh my God. Oh my God, you guys. Do you see it? Ooh. So actually the 0.1 does take over at some point, and then from then on it grows a lot faster than natural log. So when I say something like this, that's what's happening. I think I've tried it with a class doing like 0.0001, and it just, I was zooming out forever, and it wasn't even getting close yet because it takes a long time. 0.1's a more reasonable one. But do you believe that? So like, That's kind of what we're saying here. Is these numbers now are 10 to the 15th power. So it's like, it's just not it's not clear that this is really true for most of the numbers that we experience on a day-to-day basis. But if you make the numbers big enough, and that's what all these infinite series is about, is letting the numbers go off to infinity, then things like this become true. So I just want you to keep these kind of inequalities in mind when we're doing these problems, because they're helpful. I mean, you want to think about, let me share that again, sorry. Like, yeah, like, a bunch of these problems have natural logs, or, I mean, you want to think about all these tests, right? You want to think about divergence, comparisons, integral tests, but when it comes down to it, a lot of the things that when you're trying to figure out whether you think a series is going to converge or diverge, it comes down to these kind of inequalities. Okay, you guys want to try? Like, I really just want to hear your thoughts. Like, you don't have to necessarily like solve these, like solve them, like write up beautiful answers, but it's almost like, do we think this is going to converge or diverge? Could we start to give some argument? Which test is going to be useful? What inequality is going to be useful? Does that make sense? So let's do that. Let's start with number 6. Let's go into groups. Shall we do groups? Shall I put you into groups? Do you want to make your own groups? What's that?
We did birthdays last time.
Oh, we did birthdays last time. That's right. What's that? What's a scheme? It's been a while since we did that. Where you're from by in alphabetical order, like you could be a state or a country or a city. A lot of Maine and Massachusetts. Well, you could say a city if you're from Maine or Massachusetts. A town. Cities in Maine. Or should I just put you in a little? Other people are like, what are you doing, King? Just put us in the groups. All right. Yeah, you guys, but I do want people to go to boards and write stuff down and think about stuff and talk about it. So yeah, let's just do that. You guys are there, you guys there, however you want to divide up. Emily, if you want to join them, you can. I know you guys want to work together. You guys can use one of the front boards if you want. Ahmad, do you want to join them? You 3 here. You guys over there. You guys over there. Pretty much what we always do, right? Okay, and if you're on Zoom, I'll watch the chat. And you can try, and then I'll probably pause the recording. Zoom the recording. Okay, so it's good. I really like just making you guys think about some of this stuff, because it does. It's a subtle line of reasoning, and it's kind of worth I was trying to give you the indication here of the kind of things we can do. But as I was going around the groups, it's definitely, it takes, I don't know, there's a lot of different thoughts, a lot of different steps to the thought process and things that have to occur to you at the right time. I mean, that's kind of what learning or knowing how to do something is, being able to ask yourself the right questions at the right moments to be able to keep making progress, And so it's just training. You just got to do it enough times that it starts to become, like I said, this is stuff that's counterintuitive. So we're trying to build some sort of intuition, but it's not natural. So you kind of have to do some work. So let's talk about some of these. So number 6, most of you, so I'll just write these on the board because I'm on the Zoom. And maybe we'll try to be a little more rigorous about the arguments. So 5 to the n plus n squared over 6 to the n. And a lot of you said, okay, the n squared should be negligible compared to the 5 to the n. So the informal idea is that we can really just ignore this pretty much. It's 5/6 to the n, that's geometric with r less than 1. Feels like this is going to converge, right? But maybe one way to justify that is to say, well, we could actually just directly compare n squared to 5 to the n, right? We know that's true. And so then a lot of the steps of this also, and it happened when we were doing comparisons of improper integrals too, and comparisons of series, is that you kind of want to build this expression and exploit this inequality to have this compared to something simpler, right? So if you do that here, you get 5 to the n plus n squared is less than 5 to the n plus 5 to the n. But that's just twice 5 to the n, right? And then if we divide by 6 to the n, because I'm trying to make this expression, 5 to the n plus n squared over 6 to the n is less than 2 times 5 to the n over 6 to the n. By the way, since we already sort of convinced ourselves it's going to converge, it is nice to use an inequality like a less than, because we want the thing on the right to, we want to be less than something that converges. Right? We want our unknown series to be less than a series that we know converges. And that will mean that our unknown series converges. And so a lot of you guys were skipping all these, or even when I was on the boards with you guys, I was sort of skipping these steps, but like, you're adding a bunch of things, and if they all satisfy the inequality, then the sum satisfies the inequality also, right? But now what is this series? I could pull the 2 out and then write this like this. And so this, now we are actually using the fact that we have compared directly to a geometric series with r less than 1. Geometric, r equals 5/6, which is less than 1. So it converges. And therefore our original series converges also because it's less than. This is the stuff you have to really ask yourself, does every step of this argument make sense to you? I mean, I admit, like, the first step might feel a little bit unmotivated or something, like just kind of pulled out of nowhere. And that's the part that having experience, you kind of have to build experience, but also just the fact that we sort of analyze this informally and figure the n squared's negligible. So you can sort of start to convince yourself to start with steps like this. Right. I mean, there's other ways I can imagine doing this too. Like, you could try to argue the entire numerator is less than like 5.1 to the n, if you wanted to. And then the whole thing would be less than 5.1 to the n over 6 to the n, which still is geometric with r less than 1. I could see various ways to go about this. But if I wanted to sort of give a justification, this would be it. Okay. Questions about that? Okay, 7 and 8 are pretty quick. 7 is that square root of 1 over square root of n squared plus 1. Most of you didn't spend too long on that because it's kind of, you kind of know now what to do, right? Like, again, the informal analysis is what? Someone tell me what informal analysis you came up with. Yeah, Maggie.
1 over n.
Yeah, the plus 1 doesn't really matter. So 1 over square root of n squared is like 1 over n. So this should behave like 1 over n. So 1 over n, diverge. Actually, if you wanted to be a little more explicit about it, you could use either of the two comparison tests. You could either try to, compare, in fact, we did stuff like this where you could try to compare this directly to, like, you could show this is less than 2, the bottom, like, you can use that limit comparison test thing if you want, although it's kind of interesting, but let's just say, like, again, you'd want to build the expression, right? So like, what can we say? We start with the n squared plus 1, right? What could I say that's between? N squared, what could I put there? Remember when we use the constants? What's a constant I could put here? 0.1? Does 0.1 work? Yeah, 8's a good constant. 8n squared, or 10n squared, or 2n squared, or whatever, right? In fact, let's just, you're right that 8 is a good, but like one thing is like, you could say n squared plus 1 is less than n squared plus n squared, if you wanted to. But right, so I can sandwich this between these. Actually, let me use a perfect square. Since I'm going to take the square root, let's use a perfect square. Right? So that means if we take the square root of all of these, because I'm trying to build this expression, right? I guess this is really just n, and this is just 2n. And then I turn them upside down, and that'll flip the inequalities. Like that, right? Because I can either make these greater thans or I can just rearrange. Does that make sense? Now you put the summations, and the 2 can come outside. So, you know, you can do both sides. You don't really need both sides. Actually, you do need, am I doing this right? Yeah, okay. Yeah, like this actually doesn't quite, if I just compared it directly to n, then this inequality wouldn't be enough. Because knowing this diverges, but this is smaller, doesn't tell us. Right, those are some of the, like, it's almost like I almost want to write out like language you should tell yourself, like, or statements you should try to convince yourself to believe. If I have a series that diverges and I have a series less than it, then I cannot conclude anything about that series. You believe that? But this series also diverges, and the series we are analyzing is greater than it. So it has to diverge. But it's either way, kind of the way I did this to not have to worry about that was just to stick it between two things that both diverge. This diverges because I can pull the 1/2 out, and it's the same series, the harmonic series again. So this diverges. Okay. Again, like there's the informal argument, and then there's something slightly more formal. Okay, but let's get into, it's funny, I saw people doing different things with number 8. What's really going on with number 8? What kind of series is number 8? So this is funny, I like this. You can definitely give this argument that you guys gave, which is that, right, the bottom's growing really fast, so we expect it to converge. And you can even say, well, e to the n's bigger than n squared, so 1 over e to the n's less than 1 over n squared. Compare the series. We know this series, if we put the summation sign here, we know this one converges. So that one has to converge. But also, even more simple, it's geometric, right? This is the same thing as 1 over e to the n, which is geometric with r equals 1 over e, and e is bigger than 1, so this is less than 1, right? Does that make sense? But I still like this, that's nice. I mean, that's kind of like, in some ways, this is, you can see why geometric series converge when the r is less than 1, because you could always compare to like the 1 over n squared series. Because certainly exponentials grow faster than n squared. So converges. Okay. So being able to recognize geometric series is a good thing. Now, number 9 was interesting because I definitely had interesting conversations with people at number 9 and number 10. Actually, 9, 10, 11, and 12 are all interesting. Maybe we can do those definitely. And we can think about some of the others. But yeah. So there's an intuition with number 9. I started at n equals 2. I think I started at n equals 2 just because natural log of 1 is 0. It almost never doesn't really matter where we ever start our series. I can start them at n equals 100 if I wanted. It's really as you go to infinity that you care about. So like, again, there's an informal notion. And what I just erased was that the natural log grows slower than any power of n. So we talked a little bit about it's like, do the terms go to 0 rapidly enough? I had some conversations with some students about that. The terms go to 0 rapidly enough. Bless you. In fact, if I just say versus this one, I mean, these are sort of interesting to look at the difference. Right, that was number 3 on the handout. Here, we could basically say this goes to 0 about like 1 over n goes to 0-ish. So this is sort of like, but this grows. But here we had this was greater than 1 over n because natural log grows. So that diverged. Here, well, you could immediately get that this is greater than 1 over n squared. But that's not helpful, right? Because this converges, which means we don't know what this, having the inequality this way doesn't tell us anything, right? So that's the first thing you could do is say, oh, let me compare it to that. Well, that doesn't tell us anything. It told us something here because this diverged and this is bigger, right? So this converge, but that implies no conclusion. Okay. Well, so then let's start using some of the other inequalities. So then I was saying, you know, what about ln of n is less than n? I think there's just an interesting, you know, there's some interesting attempts you can make. And then you can see what happens. Like, so if ln of n is less than n, again, this idea of building the expression is important, I think, right? So I'm going to divide both sides by n squared. And you get 1 over n on the right, which means that this sum is less than the harmonic sum. But again, is that helpful? Being less than the harmonic sum? What is the harmonic sum? What does this do? It diverges. Being less doesn't tell us anything. So this is still not the right inequality, not a helpful inequality. And you know, that's okay. We're sort of honing in on something. That's the thing about math. It's supposed to be like an exploratory process. It's not supposed to be just a recipe. I do this, and the problem's solved. Like you're trying to understand how this works, right? Okay. But we can try something stronger, right? And then you can sort of decide how strong you want. Like, I think you could actually convince yourself that root n is good enough, or really any power. As soon as you make this power a little bit smaller than 1, even if I made this like 0.9, I bet you could convince yourself that this would be bigger than 1 over n, like this would be 1 over n to a power bigger than 1. And then that all of a sudden becomes helpful, right? Because we know this, by the way, just the p-test should really be, you know, at your fingertips, that it converges when p is greater than 1 and diverges when p is less than 1, less than or equal to 1. You need to have that like almost instantaneously in your head because that's the thing that like that's gonna guide you in these kind of problems, what to compare it to, right? So let's try, we could try square root of n, we could try into the 0.1, we could try into the 0.0001 if we wanted to just hit it with a big hammer. So let's just say like into the 1/2. So that would imply if we divide both sides by n squared, and now if we subtract the powers, it's negative 1.5 power, 1 over n to the 3/2, right? And now we put the summations in front and we're good. This is p greater than 1. This converges. So, yeah. Therefore, this converges too. I could get really insidious here. I could have put like into the 1.01 here, and it could still converge because natural log of n can fit in. As long as there's some gap between it into the first and into the wherever you are, the natural log can slide in there and fit in because it can be fit in less than any power of n. I think once I was mean on a test and put natural log of n over into the 1.1. And it does converge. It's the same argument. You just have to pick a strong enough. You just have to pick like into the 0.01 or something, and you're done. The same argument works. Does that make sense? Okay. But I mean, there is some feeling, yeah, like there's some feeling that this should converge. When you look at this, you should feel it's going to converge because it's almost like I know that 1 over n diverges, sorry. I know this series diverges, but I know as soon as I make this power a little bit bigger, it's going to converge. And so there's a whole 1 unit of wiggle room between n and n squared. Does that make sense what I'm saying? Like, I have a whole 1 power of wiggle room, like into the first versus n squared. 2 versus 1 is 1, like 1. The difference is 1, right? So I've got a whole extra into the first to work with here. So I can just put this. So I know that this is this converges, this definitely converges. So like sticking the ln in over on top is not going to hurt it that much. That's what I'm talking about when I'm saying building intuition. It's strange, but you can sort of start to make these kind of arguments to yourself and convince yourself of these things. Okay, but and then similarly with number 10, I think you guys had a good argument back there. Yeah. So again, I think I want to start with 2 because natural log of 1 is 0 and I don't want to divide by 0. Yeah, you guys back there, you said yeah, you basically said that this expression inside the sum is going to be bigger than 1 over n. And if you think about it, you could, again, convince yourself informally of that like, it's all about how rapidly, like if something goes to 0 at the same rate as 1 over n, it just barely, the series just barely diverges. But if it goes to 0 a little faster than 1 over n, then the series is going to converge. Think about how fast this goes to 0. Natural log grows really slowly, which means natural log squared is still going to grow slowly, which means 1 over it is going to go to 0 quite slowly. So again, informal is that like natural log of n squared grows slowly. So 1 over ln of n squared goes to 0 slowly. So this probably diverges. And you can almost work your way backwards to figure out what to compare to, because that's the thing here is like, actually with these, I sort of was arguing forwards. And then maybe the first step feels a little unmotivated. But here, if you know you have something that's probably going to diverge, maybe you want to compare it to 1 over n and show that it's bigger than 1 over n. So like, compare, if we want to show this diverges, maybe compare to the harmonic series, which is our sort of avatar for a series that kind of just barely diverges. And so then it's almost like a question: is 1 over natural log of n squared, is that actually bigger than 1 over n? Right, because that would be what we want. That would be helpful. So you can almost go through a thought process where you're like, is that true? And then so then that would mean that would be true if and only if natural log of n squared was less than n. Which would be true if and only if natural log of n is less than the square root of n, right? If I take the square root of both sides. Again, always for n large enough. But this is true. And this is true. Right? Because we said natural log always goes slower than powers of n. So you can almost get yourself there. I don't know if that's how you guys got there, but because you kind of had the perfect thing to compare to. You saw maybe that you're going to square something, so you wanted something that's squared to be n. And then, yeah. So really, I mean, so this is kind of, again, like a thought process type thing. But then if I was going to write it down, I would start with this line and work my way backwards, right? Like, if you wanted to write a nice argument, you'd say, okay, natural log of n grows slower than root n. So if I square both sides, I get that. If I flip them over, I get that. And then I compare, and I get a series that's greater than something that diverges. Does that make sense? By the way, you could do this in an overpowering way again. Let me just maybe give this as an alternate argument. Because I'm still saying things a little bit fuzzily up there. But let's just think about this for a second. You know, or you can just always hit it with the bazooka, right? Like, it's like I said with making the constants on both sides. You can always choose like 100 and 1 over 100, or a million and 1 over a million on the constants on each side, and you're good. Something similar here, you know, I could say, or just start with something strong, right? That's a strong thing we can say for n large. And then try to build the expression in the series. So square both sides. Flip over. The inequality switches, right? And then sum. And now we've done overkill. So we have something that, what does this series do? 1 over n to the 0.02. P-test, right? P is less than 1. This actually diverges. Yeah, this diverges. So kind of if you start out with something pretty strong, you usually get there anyway. So if you start out with a strong inequality, you usually get what you want. And so this diverges. Okay. Last couple things before we run out of time. We still got like 8 minutes, but I don't want to keep you maybe too. I'll let you go a minute or two early. Because I would love to talk about number 12. Number 12 is interesting, but I'll just say for 11. '11 was kind of devious. Who got number 11? People over here get number 11. You guys got it. Yeah, what happened with number 11? Yeah, what happens when n gets large? When n gets large, this becomes like 5 to the 1 over big. This goes to 5 to the 0. So it goes to 1. So the terms actually go to 1. So they actually approach 1. So limit as n goes to infinity of 1 over 5 to the 1 over n is 1 over 5 to the 0 is 1. So test for divergence says this diverges. The terms don't go to 0. Remember, this just means you're adding 1 over and over again as n gets large. Says the series diverges. Okay. Okay, now let's just look at number 12 for a minute, because this also fits with like 9 and 10, right? So 12 is the sum 1 over n times natural log of n cubed. N equals 2 to infinity. So how is this going to behave? Is it going to behave like 1 over n? What can we say about natural? Like, can we use one of these strong statements again and try to build something? This one I claim is not super obvious. But what if we try, let's try sandwiching natural log of n less than n to the 0.01, but also it's bigger than 1, right? So we know we can sandwich natural log of n in between those. So those are kind of strong things we can say. So we want to build this expression. Build the expression. So let's cube all 3. So 1 is less than natural log of n cubed is less than, I'm going to add an extra 0. If we cube this, we get 0.003. Is that believable? I want you to think about this. This one is just fascinating to me. Okay, then we do n times, we want n log n cubed. So multiply by n. We get n is less than ln of n cubed. What happens to this when we multiply by n? What power does it become? No, I'm multiplying by n. I'm not squaring. Squaring would be make it 0.06. 1.003, right? You're just adding 1 to the power. 1.003. Flip over. That reverses all the inequalities. So now the 1 over into the 1.003 is here. Oh, I forgot to put my n in there, sorry. N log n cubed less than 1 over n. And now sum. And see what we can conclude. What is this one? What does this one on the right do? What does that do? Diverges. What does this one do? Converges. This is in between. Uh-oh. Uh-oh. No conclusion. It's exactly bad on both sides, right? It's less than something that diverges, but it's bigger than something that converges. So we don't know. I can make this tower tinier and tinier, and that would make this 1 point tinier and tinier, and it would still be the exact same argument. So it's really trapped. It's really on this line. It's like, this is really on the line between convergent and divergent. Turns out, the only way to really do this is integrate. This is an integral test problem. Because we really can't, the comparisons are always going to give us no information. It's always stuck just between where the p-test flips. This is why I find this a very fascinating example. But you can integrate. Because that's kind of like the last refuge. Like if you can't, if nothing is working, then just try to integrate. So let's just do that real fast and then, sorry, I know I shouldn't have said anything about letting you go a minute early because I knew that wasn't, somehow that never happens. Sorry, we're almost done. So try integrate. Try the integral test. So now if we look at the integral from 1 to infinity of 1 over x ln x cubed dx, you do have to give the arguments that it satisfies the criteria of the integral test, that the terms are going to 0 and that, I'm sorry, the terms are positive and decreasing, but you can convince yourself the bottom is increasing. So whenever it's decreasing. This is actually pretty easy to integrate. In fact, let me do the indefinite integral first. So we really get 1 over u cubed du, just doing the natural log substitution. And so this is minus 1 over u squared. Wait, is that true? No, wait, what am I doing? I think I just differentiated in my head. Plus 1 divided by 1, negative 1/2 u to the negative 2. Is that what I wanted to say? That's negative 1 over 2u squared plus c. So this thing, the integral from 1 to b of 1 over x ln x cubed dx is, oh, this was minus 1 over 2 ln x squared. So this is minus 1 over 2 ln x quantity squared from 1 to b. I'm sorry, from 2. Actually, I need to start at 2 because ln of 1 is 0. That's why I started that at 2. That's from 2. And so we get minus 1 over 2 ln of b squared minus negative 1 over 2 ln 2 squared. So basically what I'm trying to show in running out of time is that as b goes to infinity, this term goes to 0. So the whole thing converges. Converges, and thus the series does too. Sorry, I couldn't help myself. But so it turns out this converges, but it's like the comparisons actually exactly don't work. It's like somehow in this really gray middle ground. And the only way to solve it is to actually integrate. Okay. Sorry, that was kind of quick at the end there, but I just wanted to get that example in. Just this is the more important thing, is that just like all the comparisons don't work. And then sort of your last refuge is the integral test. Okay, all right. If you could erase your boards before you leave, I'd appreciate that. I'll stop the recording. Sorry for letting you out on time.